Okay, we're now recording, and Amanda's going to walk us through how to reduce data files and start with some samples that we took on previous night.
Okay, so here, this is the notebook that I posted in the All Sky Slack channel. And it's for a McQuan Scholars Workshop. And I guess you guys are all kind of McQuan Scholars because we're using SEO, which is Mac McQuan's telescope. So this is appropriate. So basically, this tutorial is more practical than, or not more practical, but less theoretical and more data driven than the first one that I showed. Okay, so we can start. So Pylab inline imports NumPy and Matplotlib, and PIL is just a imaging module. So let's import those. So it populated the interactive namespace from NumPy and Matplotlib. And then these are just all other packages that we're going to use, and I'll show you. For now, we'll just import them, but I'll show you how they are used later. So we import them. Okay. Okay. So now what you want to do first when you're trying to reduce data is to actually look at your data, right? Like you don't necessarily know like what it's going to uh what it is before you look at it. So let me, what was it called? The folder M51 data reduction. So you take the path, downloads 51 data reduction, and then let's take gband. Okay, so this is just like, I call this variable science image path G, just to tell me like I created this label myself. You can call it whatever you want. You can just call it GSci or whatever. And I wrote down the path to the image. So type the path to your image. And then you use this fits.open. So we just imported this module astropy.io.fits. And so we use this module to open the image. And because this is a fits image, it has multiple different like pieces in it. So like, let me show you what I mean by that. So if I open this and I just print scimg, you'll see that it has one file, but a fits image could actually have multiple files. So that's why we index it 0.data. So if I place 0 here, it's the same, it only has one image. And then if I do .data, it gives me an array of numbers, right? So let's plot this. So what's a good, let's see, bmin equals 0, bmax equals 1000. Too much. 10,000. Okay. Some point you're gonna see the image. Okay, there it is. So let's make the figure bigger. So figure fig size. So this command just tells you, oh, I want the figure that shows up here to be bigger. So there it is. There's our image. Let's see, maybe if I put 100 here, it'll, or 1,000. Yeah, okay. Well, let's try to make this. Okay, so there's your image, right? So what is an image actually? Like, what does it mean for something to be an image? We talked about this last time.
You mean in the last meeting? What we've done always?
No, like what is the definition of an image? Like an image is just numbers, right? But what kind of, like in what format?
In pixels.
Yeah, they're pixels, and pixels are just a 2D array of numbers, right? So you have like a 2D matrix where each pixel has a value, right? So when you actually print out the pixel values, you can see that it's a 2D array of pixels that have particular values. So you saw that I was doing this like vmin, vmax thing. And all that says is we want to make the darkest color 1,000 and the brightest color 1,500. So the reason I was playing around with this is to get the image to show up in a way where you can see the galaxy. So a better way to do this, instead of guessing like I was, is you can make a histogram of the data. So if you do plt.hist, which is the histogram command, and then psi, so we called the array, like this dot data, like we printed it here. So this is just a bunch of numbers, right? We call the array psi mg, right? And then because a histogram is a one-dimensional or two-dimensional array? So if an image is 2 dimensions, a histogram is 1. And so because the image is in 2 dimensions, we need to flatten those dimensions out into 1. And we can create our histogram. And let's change the bin size. Okay, and let's take it out from 0 to 5,000. Okay, so we can change the limits of the x-axis from 500 to, let's say, 1,500, all right? Okay, so we see that the pixel values of this image go from around 900 to 1,100. So now we can use this to actually visualize our image. So let's put here 900 and here 1,100. And now you can actually see the galaxy. Make this smaller. Wrong way. Okay. Any questions? So I was able to use, so what does this represent? Can someone tell me? Am I going too fast?
Can I answer?
Sure. Yes.
Okay. Okay. I think it represents the histogram represents where you have the bulk of the allocation of pixels.
Yep. Exactly. So where you have the bulk of the allocation of pixels. That's exactly right. So you have most of the background is here because it's like most of this image is background, right? So most of it is here. And then your bright stuff is here.
Yeah.
Yeah. Let's make this even smaller. Thank you. Oh, there's a chat. Oh, okay. You can also like change the Y scale to be log so that it's easier to see because there's a ton of pixels. So if you want it in log, you can now see it better. Does everyone know what log scale is?
I think it has to do with the natural logarithm, converting the figures to the natural logarithms so that you see them more discrete than before.
Yeah, it just, exactly. It
so
just,
the more discretized, the more.
yeah. Yeah, exactly. It just changes the scale. So if before we had like 1, 2, 3, 4, 5, kind of like +1 or +1,000.
Yeah.
Right? Now we have 1, 10, 100, 1,000, 10,000, 100,000, 1,000,000. So it's really useful when you have a large variety of different amounts of pixels. So like, let's say, since the background is like many more times larger than the galaxy itself, when you don't have it in log scale, it looks like this, and you can't see anything, no information about the bright pixels. But when you put it in log scale, just because there's so many of them, it totally overwhelms these pixels. When you put it in log, you can see it because the scale is different. It doesn't go like 10, 20, 30, 40, 50, 60, 70,000. It goes literally 1, 10, 100, 1,000, 10,000, etc. So it goes in powers of 10. So now you can really see where, like, again, like this is the background and all of this are the really bright pixels. So this is where the galaxy is. And this is where the background is. Does that make sense?
Sure, it makes sense.
Yes, it does.
Makes sense.
Okay, great. Thank you. Yeah, I need feedback. So keep talking to me. Okay, so this is our science image, right? But you can see that it's pretty noisy, right? It's like not very smooth. So we need to reduce it because this is the raw image. So the 3 calibration images that we have are what?
We have the bias, the flat, and the dark
Exactly.
calibration.
Yeah, thank you. So the dark image, so this image is not science ready yet, right? It's kind of noisy. So the dark image is an image when you take with the shutter closed. But even though you close the shutter, your image isn't 0. It characterizes the noise of your camera, right? So let's look at our dark image. So first we have to tell the computer or the program, where is our dark image? So let me find it. Downloads M51 production. And I'm going to take the master dark. Okay. And then it's the same process, right? Let's do that. Okay. And let's make the graph bigger because I like them to be a little bigger. Okay. So you can see that it's sort of uniformly noisy. Like it's not 0, but it's noisy kind of everywhere, right? So now we have the dark, and then we can look at the bias. What's the difference between dark and bias?
Well, I can't be too certain, but I just think it's since the dark is with the shutter closed, the bias may likely be maybe with the shutter open,
The
or
bias is closed.
okay, is this still closed?
Mhm.
Okay, maybe just go ahead and tell us I know what the images look like, so, and I can always say when doing our calibrations, like in the yesterday, Matt was asking. So he said there was this shadow on one of the images. So he was asking the kind of calibration we're going to use to do, and I need is a flat calibration that I'm going to use to remove the shadow from the background. So
Yeah, that's right. But so that's the flat, right? So the dark is you take the image with you take the image with the shutter closed with the same exposure time as your image. So if your science image, if you observe a galaxy for 50 seconds, then you would take a dark for 50 seconds. And that's just to see how much thermal noise accumulates in the CCD during your image exposure. A bias is also taken with the shutter closed, but it is a 0-second exposure. We can't do 0 seconds, so we do 0.1 seconds. And it just tells you how to offset your 0 so that your background is 0. So what do you expect if you had an ideal image, right? What value would you expect your background to be?
Sorry, could you come again?
Yeah. If you had an ideal world and you had a perfect image, what pixel value, what contribution would your background have?
You wouldn't have any. If you, I'm not getting the question, but if I understand what you mean. You mean if you have an ideal image, like a perfect image,
Yeah.
what contribution would the background where the image is stationed have on the image? Is that what you mean?
Yes.
Ideally, it shouldn't have any effect on it if it's perfect.
Exactly. Yeah, that's exactly right. So you would have no contribution, right? If you had an ideal image, your background would be 0, right? So that makes sense, right? Because you want your signal to be maximum and your background to be 0. So what the biased, but when you think about like the internal workings of a camera, you can't have a negative like volt. So you know how the background has fluctuations, right? Because we're not in an ideal image. So it fluctuates around 0, right? But we can't have a negative signal, right? Like just due to the mechanics of how like the camera sums photons to each other, right? So you can't sum negative photons. So what the bias image does is it just moves whatever floor the CCD has, and it moves it to 0 so that you can have negative pixel values, because otherwise you won't have negative pixel values. And you want your pixel values to fluctuate around 0. You want the average of the background to be 0. If that doesn't make sense, maybe Adam can explain it in a better way.
Well, I think it makes sense.
Okay.
Or maybe to make sense again, if maybe there's another explanation to that.
Yeah.
Yeah, I don't really know how to reword it other than just you're gonna have that background noise, and ideally you'd want it to be 0. So that's why we take those biases, right?
Yeah. So yeah, you want your background to be 0. We know that it can't be perfectly 0, so it has to average 0. If it has to average 0, that means that there should be, for something to average 0, the constituents of your average have to be positive and negative around 0, right? So that your average becomes 0. You can't have negative photons in real life. So what the bias does is if your floor of your CCD is 40, right? And let's say your pixels fluctuate between 30 and 50, right? Around the average, then your bias will bring that down to 0. So now your pixels will fluctuate between -10 and 10. So it's just a way to calibrate the image so that your background is on average 0. Okay, let that marinate in your brain a little bit. Okay, so let's look at our bias. Okay, so this is what it looks like. And take into account also the CMAP here. This just tells you what color you can have, so you can change it to cold. Oh, cold is not cool. Cool is the word, yeah. So you can make it pretty gray. Oh, that spelling of gray. This is spelling of gray. Okay, so this is just to play around with. There's like a whole list of these color maps. Viridis, so it's like the most popular one. Okay, so now we do a histogram again. And again, we have to, since the image is 2-dimensional, we want to flatten it to 1 dimension so we can have it in a histogram. And we change the scale to log again. So this is our distribution of pixels of our dark. So why do you have different, if you have the shutter closed, why do you have different pixel values? So this is a histogram of the dark frame. So the dark frame is the shutter closed. What do these higher value pixels represent?
Noise.
Yep, thermal noise. Yeah. Awesome. Okay.
Would you also refer to that as like the hot pixels?
Hot pixels. Yeah.
Okay.
Mhm.
Just making sure those were synonymous.
They're not necessarily synonymous, but the hot pixels sometimes, well, yeah. The hot pixels are like an established, like, it's like a systematic, and like the noise is kind of like a statistical thing.
Gotcha. Okay.
But yeah, you can also say cosmic rays, right?
Oh yeah, true.
Yeah.
Forgot about that.
Do cosmic rays go through the shutter? I don't know. I forget. Oh. Okay.
Amanda, I have a question.
Yeah.
Can I ask a question?
Yes. Go ahead, please. Please feel free to interrupt me whenever you want.
Okay. In assuming assuming I need to extract the actual values of the pixels.
Mhm.
Okay. Is it possible to have the actual values and extract them as and export them as CSV files?
Yes. Do
Okay.
you want it as a 2x2 array or a?
Because I'm not a professional.
Sorry. Sorry, go ahead.
Yeah, as a two-dimensional data points.
Yeah, you can as a CSV, you definitely can. So you create, if I remember how to do this, you have your 2D array, right? So you can print your dark im. What? Hello? Oh, it's because it's drk im. Okay, so these are your pixel values, right? And then you can do tab equals table. Will this work? Let's see. Oh yeah. Okay, there you go. Yeah, and then you can do tab dot write. And then you write wherever you want it. So let's users desktop pixel values. So I call it whatever I want. .csv format equals CSV. Will this work?
Okay, that's interesting.
Yeah.
So with AstroPy, it's possible to do it with using AstroPy.
Mm-hmm.
Okay, thank you.
Yeah. Okay. Any more questions? Okay. So now we can talk about flats. So Nemeka, do you want to tell us about flats?
I don't have much to say. Only know that basically gives you like a clearer image of what you have, Like we use it to remove all those background shadows, like all those noise in the background, to get a clearer image that can, for example, in asteroid tracking, like when you're observing asteroids, like if you take it, it makes you, at least if you are following the asteroid, the movement, you can possibly sight it to where it is without the influence of the shadows behind it. I know. So I guess I don't know how else to explain it. Maybe you can. But this is
Yeah.
just the much I know about flat.
That's good. Yeah, that's awesome. Yeah. So, well, how about this question? Do you take a flat with an open shutter or a closed shutter? You have a 50-50 chance of getting it right, so someone should guess.
Sorry, please, could you come again? What was the question?
When you take a flat image, is it with an open shutter or a closed shutter?
It's open.
Yeah, it's open. So in an ideal world, so you take a flat image by looking at something that is equally illuminated. So like a whiteboard or just like the sky at twilight. So if in an ideal world, if your telescope was perfect and you illuminated it with an equal amount of light for every pixel, what kind of image would you expect to have? It's in the name of the image.
Sorry, you said what?
In an ideal world, if you illuminated each pixel with the same amount of light, a uniform light, what kind of result would you expect to have?
A flat image.
Yeah, exactly. You would have something flat, right? But since your telescope is not perfect and you have different pixels respond differently to different amounts of light, so you have, this is a bad, let's see, I'm gonna put it to grayscale and then I'll change the maximum. Did I go the wrong way? Okay, you can kind of begin to see it. Nope. Okay, well, let's just look at it here. You can see I'm gonna make this like way bigger, 20.
All right, and Amanda, it's getting close to when you need to go. So if you want to wrap up here, we can have everybody else, because it is pretty well annotated. They can try and going through the rest of the process. And when you get a finished image, please upload it to the All Sky Survey Slack channel in the class education workspace. And we'll just, see what people get with when you can upload any of the bands. But yeah, if you want to finish talking about the flat field, go for it.
Wait, we're almost done to the end. We're almost up.
Okay.
Yeah. Okay, so here's the flat image. You can see that it's not uniform. And what is this? It's dust. So it's just dust that's on the camera or on the mirror. And so it looks like donuts. So we call them dust donuts. Okay, so now that you can put everything together, no, maybe you can't put everything together. I'm just gonna delete this. No. Okay. Well, maybe then you guys will have to figure this out on your own. Wait, actually, let me. Okay, let's see if that works.
It looks like it's about to.
Well, okay, we have to make them bigger. Plot bigger. Oh, 24 by 8. 30 by 10. Oh, look, the big size is there. Okay, and then we have to change the scales. So what scales did we have earlier? This is the scale.
1,000 to 1,100.
Yeah. Let's see. Okay, so we have our original image.
Hmm.
And whoa, something weird happened. Hold on. It could be like much smaller, I guess. Right after the reduction. So let's
Oh
do
yeah.
it. Okay, well, anyway, so
Play around with those values.
play around with those values and see what you get. That's it. So we'll talk about what this does next time.
Perfect.
Thank you for letting me talk a lot.
Thank you, Amanda.
Thank you, Amanda.
Yeah, of course.
I see miracles on. All right, then we'll see you soon, and I'll just give a couple updates for everybody else, and we'll see all of you next Thursday. And Nemeka, we can talk about when to schedule a meeting for all of us to talk and meet. Does Monday work for you, Amanda? If we were going to plan that, 'cause tomorrow is iffy for me.
Yeah, I can do tomorrow either.
Okay,
Let's do Monday.
Monday. Okay,
Works for you guys.
So are we doing Monday, right?
yeah, we can do Monday.
6?
Sorry,
Sure.
do we mean completion of this class?
Yes,
No.
yeah. This meeting is we're wrapping up right now. I have everything recorded and I'll have it uploaded as soon as we're done. So you can go through and you can follow step by step the notebook that Amanda went through. If you want to find any of the resources, just let me know. I uploaded everything. Amanda and I both uploaded everything that you're going to need into the Slack channel in All Skies Survey under Class Education. But other than that, we should be good. So yeah, so Nemeka, for the paper, we can discuss on Monday at 11 a.m. or 6 p.m. for you.
Yeah, that's
Okay.
it. That's okay.
Does that work for you, Amanda?
So, Adam, I will send a reminder before Monday so that most of the students and participants will hook up. I will send a reminder by tomorrow. I will send another one by Sunday, at least to get them so that they will be able to join at the appropriate time. Then I will also try, like I promised, I will try and chat them privately to know why most of them are not joining the meeting at the right time.
I appreciate that. And the more information we have, the better we can problem solve to make sure that we're making sure that we're meeting at a good time for everybody and that everybody has the opportunity to participate.
All right, no problem.
And just to
Yeah.
be clear, the meeting on Monday is just a smaller group from a publication for a paper that was presented last fall. So don't worry about the Monday meeting. Everybody else, we'll see you guys next Thursday at the same time.
All right, no
Okay.
problem.
Okay, bye guys. Happy belated birthday, Chris.
Oh yeah.
Okay,
Thank you.
have a nice time.
Thank you.
All right. Enjoy the rest of your evening.
Yeah.
Thank
Bye.
you. Regards to Kate.
Will do.